And yes, I know it's after lunch, and this is the requisite haze of fog and everything else, but siestas, is that common? And I know in the U.S. that it's still understood what siesta is. It's a little nap after lunch. It's in the afternoon. Hopefully, I can keep you energetic and awake. But you only got to stay awake. What's nice is you really only have to kind of pay attention for about 45 minutes to an hour, and then we'll have a break. So just you start your clock now and keep me honest. Conversion of sensor digital number to spectral radiance and to spectral reflectance. So I'm going to start at the end. And it's easier for me just because from a schedule standpoint, and really this, when I say I'm going to start at the end, this is the last step of the whole process. So we've got measuring the surface, we have measuring the atmosphere, we have rate to transfer, top of atmosphere, and the comparison to DN. And that's what I'm starting with now, is this comparison to DN. And that's because I can do it in about 45 minutes or an hour, and then we can get into atmosphere for the rest of the day, and then tomorrow we'll do reflectance, and we'll get into some other topics. And so it gives me a nice, it keeps the timing about right. But also it allows you to kind of see where we're going in terms of the end analysis and the end product. And our two key pieces, what's nice is we covered this towards the end of this morning. Sensor output and top of atmosphere radiance. Those two compare to one another to get us to this conversion to radiance. So reflectance. Basically we're going to measure reflectance. Technically we're going to measure upwelling radiance using a spectrometer. We're going to do that up at the test site. And we're going to measure the upwelling radiance with the spectrometer from panel. And then I'm going to ratio them to infer reflectance as a function of wavelength. And that reflectance is going to be sampled spatially. And I'll average that. So what I show here is the average. And over here on the right-hand side is the standard deviation. And this is, by the time we were mature in our processing at the University of Arizona, this was an automated output from the processing scheme that we had developed, to where you would get the analysis of what you see here, the larger standard deviation. This is 1380 nanometers. This little blip here is 940 nanometers. This feature here is 1800 nanometers. And I'm hoping that those numbers mean something to at least a few of you. 940, 1380, and 1800, and 20, or up beyond 2400. Strong water vapor absorption. So that's what, you see that doesn't panic you. And then you see and these are percent, and this is a test site, this is the small test site. There's about 5% variability of the measurement. So you take an average of roughly 600 spectra, and you get a 5% uncertainty. It means the site's not that uniform. Whether that's important, though, depends upon whether it's truly random, or whether it's bright then dark. And if it's bright then dark, whether or not you actually characterize that properly in the imagery versus what you measure on the ground. So there's still, whenever you start looking at metrics like this, there's a lot of deep information in there. And what's difficult is we put this together because we were having the students do more of the processing. And it was trying to teach them to be a little bit deeper thinking in terms of looking at the output. The yellow boxes are the rough spectral ranges that correspond to the bands that we were calibrating. So in this case, it was for, pretty sure it's Landsat 5. So you have band 1, 2, 3, 4, 5, and 7. Anybody ever wonder why it goes 5 then 7? You all know the reason? Anybody care?
I do.
You do? The original Landsat 4 had 6 bands. And it went basically 1, 2, 3, 4, 5, and band 6 was out at 10 micrometers. And then those geologists, those pesky geologists, convinced NASA and the USGS to put in an additional band for geology out at 2.2 microns. And then
Can't be geologists, they wouldn't have actually asked for such a wide band.
well,
They didn't ask for one wide band. They asked for several small bands.
well, okay.
All
now
they
you-
got is this shit.
But now you have to go back to 1983, and the best they could do, so the reason the band is wide is because of signal noise. So we had to have a wide band because the detectors were very poor. Most of you know what a fax machine is, I hope. Hopefully you've never had to use one. Copier. But you all are used to digital copies of things. In the 1970s, there were not digital copies. Everything had to be Xerox or copied physically. The company that was building it said it was going to cost an extra big amount of money to basically put and change this band to band 6 and change the thermal band to band 7. So we decided to just keep it the same way. So it goes to band 6 at 10 microns and it comes back down to band 7. Now the reason I like this story is everybody, well, yeah, it's typical. Budget guys don't want to do that. When we launched Landsat 7, we kept the same numbering sequence. Because the scientists didn't want to change their codes, their computer codes they had written. They never were looking for wavelengths, they were looking for band 7. And so we were not allowed to change it because they didn't want to go back in and change their codes. But it's important. The older you get, the more stories you like to tell. So this tells you that you're talking to somebody that's old up there, so you're going to get a story periodically. Hopefully it woke you up a little bit. But knowing what these bands are helps us get to see if there's a feature in the surface reflectors that we have to be worried about. So it ties us back to the sensor we're trying to calibrate. We also then start looking at summary output from the atmospheric retrieval. This is the inversion of the data, and what it's looking at is there's small little data points in here, and that allows us to see if there was a measurement from the solar radiometer that was far off. It also allows us to look at the values to see if they're within norms, near the average that we typically get. Looking at what happens as a function of time. If anything here is going up and down, it clouds or there's dust that's moving around. We don't like that. This is looking at the downwelling sky irradiance, everything coming from the total sky. When that's smooth, then that's also a really good day. And this black bar is the time the sensor overpass. So this gives us really, I look at this and I go, oh, this is going to be a great day. So we would be happy with the data collected on this day. It would meet our kind of uncertainty requirements. You combine all of that, so you take the reflectance, you take the atmospheric information, the knowledge of what your uncertainties are, the variability, and it goes in the rate to transfer code, and out comes the top of the atmosphere radiance. And then you do the band integration, the convolution, that was that last equation from this morning. And we do that at now several other points. This one now is for Aster. So, Andreas, you were complaining. Now you should be happy. There's many more bands out here at the 2.2. It's
Many.
Yeah.
Few.
I know you want 50, but at least there's 4. It's okay. But it also allows you to start to see where your bands that you calibrate, where they fall within the spectrum. But it also shows that the results that we're getting are not just 1 or 2 or 3 data points. It's at a hyperspectral interval. These results are now from Modtran. The original processing was a combination of Modtran with the Gauss-Seidel.
Sorry, but did you say that you resampled the data to the bands?
So what we do is this output is done at a 1 nanometer sampling and a 2 nanometer full width half max, 2 nanometer bandpass. Triangle shape type thing. And then that output is then convolved with the known filter functions of each of the individual sensors.
Because
Say again?
Because what you get out of an ASD isn't the 1 nanometer, despite what it says.
And so the assumption, so that thing we do is, we're assuming that this 1 nanometer from the ASD is, that value is representative of that individual, just single value. And again, that's the advantage of going to reflectance, is it's smoother than radiance. And so that allows that, and as long as we're oversampled, we're okay, we think. Because when you take that 1 nanometer, if you assume that's a point value, you take the radiance, you run it through the atmosphere, and you assume that's a point value, and then you convolve at a 10 nanometer or larger band. That uncertainty caused by that is so much smaller than any of our other problems that we're still okay. Did everybody follow that conversation? No? Yes. So let me translate now. So the question was, we have measurements that are at a spectral resolution that you really do not even know what the spectral shape is. To do it properly, you would take your measurements and you would take away the instrument effect and the reflectance. So you would deconvolve the spectral shape of all of the individual measurements to get to basically a sampled reflectance that is essentially a point measurement in each of the wavelengths you think you have. And then that would be combined with the radiative transfer, and then combined with the spectral bandpass of the sensors to get the true output that you expect the sensor to have. We do not do that because the uncertainty that's caused by that assumption of, well, we're just going to assume we're already at point values. That assumption does not cause a large uncertainty yet. And so far, as long as the band passes we're working on the instruments at 10 nanometers or larger, you're averaging so much over that 10 nanometers that any feature that you have will just go away. Summary outputs, basically all the inputs in terms of atmospheric conditions, temperature, pressure, ozone amounts, Modtran run parameters, so that they could have an idea of, and really it was once the result came back, you didn't want to have to go rerun everything, you would just go and, okay, well, somebody has here 6 instead of 16 numbers of levels and numbers of strings in terms of the angles of the dice code. The temperature really shouldn't have been 500 degrees, something like that. So you have a quick value that shows, basically reads the input file and puts it into a document and prints that document for everybody. And this is important because you're trying again to get to top atmosphere radiance and then convert that into something that can be compared to the sensor. So we have the top atmosphere radiance values now. And those get compared to the imager to then get to where we want the counts per unit radiance. But I need to go back and talk about the solar irradiance thing again. And so I have to then multiply by a solar irradiance curve. Modtran already gives you radiance. So you're going, oh, well, that's no problem. I don't need a solar curve. But built into Modtran is the solar curve.
Is Modtran open source?
Sort of.
So how do we run it?
Oh no, yeah. Yeah, you're open source.
Yeah, I'm open
No,
source.
no, it's not open source.
Okay. So how do we do what you're doing?
You get a license with Modtran.
You gotta buy it.
You can go back to the
Or should we use 6S?
6S will give you the same, 6S will give you the same, and that's more available than Modtran is. Modtran, if you're a US citizen, is relatively straightforward to get. You just have to get approval from your organization, go to the US government, and then tell them that you're not going to redistribute it, and then you get it. And if you want to get the easier to run version, the graphic user interface, then you pay for that. I think that will become globally available. I don't know if that's, they bury the code so deep that there's no issues with the US government at that point. So you can pay for it. With the 6S code, they have a great distribution version of that, and that would give you the same output. And within 6S, they do everything in reflectance. And so you would then have to convert that to a radiance using some kind of solar curve. But Modtran will build that in for you. You just have to pick which one you use. Where it becomes important is then when you try to go to reflectance at some point, you have to make sure you know what model was used in your run of Modtran going the other direction. Because there's 7, 8, 9 different versions of solar irradiance models in Modtran. The two I have here are WRC and Modtran based. I like to use this one. When we talked about the Fraunhofer lines already, this feature here, right around 720 or so, that's water vapor. The sun doesn't have any water vapor. There's no water vapor on the sun. So the WRC, that orange line, has it right. Modtran, what they did was they took basically some absolute solar irradiance measurements and combined them with some measurements made at very, very high spectral resolution, because the Modtran people wanted to be essentially line-by-line type calculations. So they went to the Kitt Peak Observatory, which is at about, I don't know in feet, 5,000, so 2,000 meters, 2,000 meter elevation. And there is where it's the Chance Current model. Kelly Chance is the expert in the high spectral resolution sampling. Courage is the one who ran the instrument at the top of Kitt Peak that made the solar value measurements. That's residual water vapor in the atmosphere over the site from 2,000 meters to the top of the atmosphere that they just never were able to remove from the system. So you get some kind of bias because of that. I also showed here, when I talked about this morning, is the difference between a lamp curve and a solar curve. And so this is the other reason that we like using the sun and reflectance basis. There's the difference between the two of them. But here we're more worried about differences between solar models because we're going to multiply the reflectance to get to a radiance. And this just highlights some more of what I showed this morning. At 1 nanometer intervals, you basically have all of this noise, and much of this is simply because of the differences in how they sample. So this goes back to what Chris was asking in terms of, when you do your ASDs, are you worried about these small little features in the sampling? No, because I'm not averaging over 1 nanometer, I'm averaging over tens of nanometers. All of this noise here is because of differences of assumptions in what the bandwidth was to sample, the spectral sampling, and you get them all on the same scale. So you go from the WRC and the Matran results to a comparable set that are at the same wavelength. You have to do some resampling to do that. That creates noise. So that alone can cause some hit to your error budget just in terms of how it's resampled. The way around that is everybody uses exactly the same resampling approach. The problem with that is we've now just created a bias for everyone. So one takeaway from that is, my view is you never force everyone to do exactly the same thing because you will never find if you have a bias in the way you are doing it. You're always going to all get the same wrong answer. But out at the longer wavelengths, you can see there are some large differences there. And that's what we saw this morning in the discussion.
So what kind of the irradiance model in monitor? Because the monitor has the several model.
The one I tend to use is the one that the Landsat team chose, which is the chance current, the checker.
Oh.
CHKUR. That tends to be a good combination of good absolute value. It was also the one that most of the Landsat community was using for their retrievals. So when they would go from top of atmosphere to bottom reflectance for land remote sensing, that was the model they were using. So when we did the validation and the calibration, we went with that solar model. And again, another story is, when I went to the very first Landsat 7 meeting, I gave my talk and told them all that Landsat was off by 7% in calibration in band 7. And then the person after me got up and they gave a talk and they said, I don't know what the University of Arizona is doing, we get great agreement. And I raised my hand and said, so what solar model are you using? They told me Matran. I said, well, I thought the official was WRC. They said, yes, but we chose not to do that. And I said, okay, give me 5 minutes. And I went back and just showed a new graph a few minutes later that showed that I agreed with Landsat. So without Landsat, without the checker model, I was 7% off. With it, I matched everybody else and I kept my funding. So what does it really mean? And so this is again showing some of the things I was talking about this morning in terms of percent differences and averages and 10, 50, 100 nanometer boxes and so forth. This right-hand side just shows some, how does it change? How does it change the price of beer? What's the real impact? Aster bands 1 through 9, green, red, near infrared, 1.6. Tell how long it's been, and then several other bands in the short ones infrared, and 0% is right here. And this is percent difference in each of these bands relative to the reflectance base. And each of the different boxes again are the two different solar models, a WRC model and a Matran-based model. And you can see that in some cases it can make a bit of difference, but it still doesn't really change a lot of the conclusions of whether or not you should change your calibration or not. In the lower right is an airborne system called MASTER. And I put this one here because it's far more bands. And it's really kind of interesting as to the conclusions you draw when you start to look at this shortwave infrared. The visible near infrared and kind of the middle part of the 1.5 region, same result. Everything is very similar, but now you start to go, well, this one here is this other one, which is the Matran base, if I choose that one, everything looks like it's about even with a 5% bias, except for a few bands out in the visible. If I choose the WRC, well, then I have a kind of a linear problem that seems to be changing the calibration as I go out to longer wavelengths. The real answer to that is I am drawing conclusions I should never even be thinking about trying to draw. I'm trying to find shapes where they are not there. There's nothing statistical to allow me to make those decisions. So that's, we have to be careful. We have to look at the data and not let the data, let our eyes start to say, oh, it looks like there's a picture there that I should see. But it also starts to point out that what you pick for that solar model can play a role in terms of what your answer is. And the takeaway is you just have to be consistent. So when you choose your solar model, you walk out of here and you start talking to people, step one is ask somebody else what model are you using. So my mistake when I went to the Landsat 7 meeting was not asking beforehand, what solar model should I use? I was silly and thought that maybe everybody was going to use the official solar model. I was the only one that was using the official solar model. Not a problem, you just multiply it different at the end. It's something to do at the very last step. You want to talk to your validation community, you want to talk to your user community, you want to talk to your calibration community to find out how they're actually assessing the calibration on orbit for the system. If it's a diffuser-based calibration, then it really comes down to is everything's in reflectance anyways, there's no problem with the solar model. You just make sure you're using it consistently between your calculations and theirs. Use going up and going down, it makes no difference. If it's a radiance-based calibration, so Aster, for instance, was a radiance-based calibration, it does not matter which solar curve we choose, as long as whatever we choose, we use the whole time, and the validation of the calibration is done using that same solar model. And it's all built in. And if that means that we end up with a 7% calibration change that we have to make, you make it, but then that's basically because there's a difference between the laboratory calibration relative to that solar model. That's the only cause of it. It's a common issue. So it really is just making sure you're talking to all of the other users in terms of that. So do not, this seems to be a favorite discussion in on-orbit calibration of what solar model are you using. And I've gotten much better at just saying it doesn't matter. You tell me which one you want me to. Because it forces them to start asking more questions that you can then demonstrate that they need to really understand the problem a little better before they start assessing where your dominant error source is. So at this point now we have the spectral radiance, because we've multiplied it by a solar curve. We've got it for the predicted bands that we want. So now what we need to do is compare it to the center output and calibration coefficient. And that's partly now we start to get into, and I'll talk a little bit more about this, is if you compare the spectral radiance from the center, now you're doing a validation. If you count, so you're doing a calibration. And realistically, the only difference between the two is how you're being funded to do that. You'll still come to the same conclusion. What's nice is the sites that we're using, you can use pretty much, when we talk about this, any level of data product you want because they're uniform enough. I prefer to take something that's closer to what the user community is using rather than something closer than what the instrument community is using. And the TARPs, again, they allow you to mark the edge, and that allows you then to get the average and the standard deviation. But I still would always move my site around. So you think you know where you are. What you want to at least do is assess what is the uncertainty because you're in a different place. Either your ground measurements are not where you think they should have been, or your pixels are off. So for instance, let's say MODIS. MODIS has a 500-meter pixel in some cases. And I'm trying to match it up with a measurement on the ground. I could be off by 250 meters and still be okay with MODIS. I would never know it. So you want to at least understand what the variability is in your site as you start to do that analysis of the counts or analysis of the radiance from imagery. So it's straightforward. It's basically, you have your image, you know where your site is located, come over here and we know. What's nice, the other reason I like this is we could always, even if it wasn't high resolution, is you can tell the difference between the black and the gray, and you can then say, okay, I'm going to take the center of the gray and the center of the black, and I now know where my site is. I have my DNs, I have my counts. And then I would use those counts to then compare to the radiance to get to a counts per unit radius. And And the same thing, I've shown this a couple of times, I can do it just by looking at the imagery. I'll skip that for now. And some of these I repeat them just so that they're all in one place. So as you start to go through these charts, you can pick out, everything will be self-contained when you have them in your own hands. What type of data? Just repeat this once again. The one thing I'll highlight is if you go to a higher level data product, you can usually get away with not having tarps. You can just go geolocation and you're okay. You can always go back to the raw imagery if you really, really want to. I do not advise it at this point. DN to radiance conversion. Now I apologize that now I'm going to go way back on the scale of what I think you might or might not know, but I want to make sure we're at least all in the same place. So the idea is that when we do a calibration, the goal is that we have some number or set of numbers that allows us to take the output of the system to go into some kind of radiance that was input to it. Either it's radiance versus digital number, or it's digital number versus radiance. Either one. I see the left one easier because I can see where saturation happens. So when I hit saturation, everything goes flat. It bothers me when I see it vertical. But physically, this right-hand graph is the correct graph that you really should be looking at in terms of your input radiance and your DN output. But either way, and in this case, the offset is 0. And all I would do is, from my sensor, I would get my DN counts, and I would have my radiance, and then that would give me a ratio and just give me counts per unit radiance. And that's my calibration. So in this particular situation, I could grab any of these and assume that they might be from my reflectance-based calibration. Hopefully it's not these up here because that's not usable. But somewhere along this line I would have a value. And the same thing I can do in the pre-launch, so this is exactly the same methodology. And from that I can basically figure out that I have a 2dN watts per meter squared per steradian, or it could be half of a watts per meter squared per steradian per dN. I can either do it as counts per radiance or radiance per count. One of them gets smaller as the instrument gets worse. So basically, as the response of the system gets worse on orbit, let's say we have a degradation, one of those will get smaller. The other one will get larger. Sensor people like to work with the one that gets smaller as the sensor gets worse. The way to think of it is, for a given radiance, if my sensor degrades, my output is going to go down. So my counts per radiance will go down. The user community would rather have radiance per count. Anybody want to venture why? Multiplication is easier than division. And in the old days it was. It took more bit flops on old computers to do division than it did to do multiplication. And we could never convince them just to flip it beforehand and then put it in so they could just do the multiplication. So when you're talking to people, you have to be careful that you know at least the units. It's a strange thing to have to talk about. But again, make sure if you talk to the sensor person, it'll always be counts per unit radiance. But if you want to give it to somebody who's going to do the conversion to a data product, they'll usually want it the other way around. In some cases, you may have an offset. In fact, I take that back. What's interesting now is almost all of the data products being delivered today will be delivered as a zero offset situation. The instruments themselves are all designed purposely to have offsets in them. We want to know when we hit 0. So they'll always be built in with an offset. But the processing now, and going from a raw data stream into a process level 1, removes that. And it just provides the user that with a game typically. And there's others, like some of the commercial systems are providing fairly complicated formulas, but usually now you'll see just a simple game term that you'll have to convert. That doesn't affect if you're doing reflectance based, because the product you're getting will already have gotten rid of the offset. But if there's an offset, it just means you have to make sure you get the units right. So the mistake you can make is sometimes you'll get an offset in radians, so you have to divide, you have to take it out on the other side of the equation than on the count side of the equation. So you just have to make sure you know what the units are for your offset. And then in the cases that you have nonlinear systems, I would advise you not using the reflectance-based method. Because the one thing about the reflectance-based method is we have no easy way to determine nonlinearity. And in that matter of fact, in the shortwave, in the reflected part of the solar spectrum, I know of no way to do nonlinearity studies using vicarious methods. Maybe in 10 years we'll have something, but nowhere in the near future. So if you have a nonlinear system, either try to work in a part of the spectrum that's fairly linear, or just stay away from it. So just to reiterate on the counts per unit radians, CPUR, counts per unit radians, or radians per unit count. It just depends on what you're trying to do. Both of these are calibrations. That's the nice thing. This is a true calibration. If you are determining these numbers, you have calibrated the system. Sensor engineers prefer counts per unit radians because it gets smaller when the system gets worse. That's the big reason. There's other methods. So a good example is Aster. If you use Aster data at the level 1B and beyond, they never change what you see. They do all the modifications on the pre-processing so that the coefficients that you have in your hand are always the same in the state of it. They call them universal calibration or conversion coefficients. And those numbers never shift. That's a nice way to do it. It basically removes all of the uncertainty for you. It hides everything. So if you want to figure out if the system's degrading with time, you have to go back to the 1A. If you want to do a validation, you can use the 1B. So I've used this term validation a couple of times. There are many people who say you can never validate. I'm not one of them. I don't mind. This is a fine term to me. Another way you can calibrate is through the validation by looking at the accuracy and the precision of the data product. You can either look at retrieved reflectances and see if it matches the real values. By real is you have retrieval and reflectance, and you can compare it to the measurements. If we're within the accuracies, that's validated. So you know what the uncertainties are for one, you know the uncertainties for the other. You combine them, compare them, and if they all agree within those uncertainties, everybody's happy. The amount of chlorophyll, though, is an interesting one in terms of how they do the processing. The ocean color community, they never really calibrate, and they never really validate. What they do is they tune their retrieval algorithms for chlorophyll to match a buoy system. It works great for them. It's fine. But it's not similar to what we're talking about here, where we're actually going to do a calibration to understand the sensor as opposed to the sensor plus the atmospheric correction plus the retrieval. And then, yeah, just more of that. In terms of radiance validation, though, if you have the counts, then you're going to get a calibration. If you have the radiance and you compare your predicted radiance to their predicted radiance, you're doing a validation, and that's just as good. That's going to be useful to somebody, because somewhere somebody will learn that they have to change the calibration, which is giving them their validation. For a lot of people, that subtlety is a big deal. For others, it's just terminology. But it's just, I want to make sure you saw that before we went too far along. Some example results, counts per unit radians. So these are level 1A data from Aster. And you've seen this a couple of times where it shows a bit of a probable degradation. The scale is the same in both of these. But you can see that the two systems the two bands have slightly different degradation rates than each other. If you had done this in 1B, you may not see that degradation. You would see it as a radiance validation change, or that in fact the validation is agreeing as a function of time. You can also then compare to onboard calibrator information. So this is nice, is on the Aster instrument they have a lamp set. These are all three of the bands in the visible near infrared telescope of the system. The large symbols with the larger number of sampling are the onboard calibrator data. And then you have the vicarious calibration results. And these are just from my data set. We have other data sets from Japanese colleagues that I could have put on here as well. they did not disagree much from this. It's just easier to have the one data set there. And in some cases, we also have done this now in terms of a Lotus-Aster cross comparison as well. So we've done this reflected space, and we've done this as a true comparison. In some cases, there's not that agreement, but in others, you start to see disagreement as we go on in time. And so the question then becomes, is at what point do you say that there's now a true significant difference? And in the case of Aster, it took many, many years for us to finally settle in on, well, I think we need to consider having a new calibration coefficient. These results are just Landsat 7, Landsat 5, and it's just showing again possible cross-calibrations between the two instruments in order to try and find out what would be the appropriate way to combine the vicarious data. But again, so what's nice is it's an example of gains, an example of counts per unit radians. So true calibration determination. So what this should show is that there's a lot of steps here. It's very simplistic in its approach. You have an image, you compute average counts. You have a rate to transfer code, you have a predicted radians. Take the ratio, we're all done. Maybe it's complicated, I have to do an offset correction. It's still pretty simplistic. But there's a lot of subtleties in this. Big thing is we have to know what we're trying to get to in terms of how good of an answer. As I mentioned, it took a long time before we changed the Landsat values. Even when we start to look at the uncertainties, everybody goes, let's get one more data point. Let's get one more data point. And that's part of the problem. The bigger problem is how do you get your information across? Once you have this answer, what do you do with it? So the Aster community is a good example. Is we early on the science side said, there's something odd here. And on the official side, nobody wanted to make a decision. So we just started publishing results on the science side. And we made sure, at least through the peer-reviewed literature, that people knew if you want to use bands 1, 2, and 3, band 1 needs to be corrected by this large amount, about 10 or 15% change. And then eventually the processing scheme worked and caught up and it corrected that for us. I keep telling people is the best way to fix it, though, is just build a perfect sensor and then none of us have to do it. The other reason I put this in is make sure that I can tell if someone's still there.